Okay, my name is Benjamin Fowler, and over the last few months, Dr. Krakow and I have been studying the potential for aluminum-zinc and aluminum-germanium alloys as solvents for silicon clathrates. The aim of this experiment was to analyze the thermodynamic properties of both aluminum-zinc and aluminum-germanium alloys in combination with silicon-136 clathrates. And we're also going to determine the most efficient solvent, which would be, in our case, a metal alloy, for the crystallization of silicon clathrates. And these clathrate crystals could provide excellent electrochemical properties. And the heat capacities of various alloys are also determined using differential scattering telemetry and thermogravimetric analysis. These alloys were prepared by melting appropriate amounts of elements together, and this had to be done under inert atmosphere in a glove box, and usually under argon in our case. The metals were placed in a graphite crucible and heated up to about 500 degrees Celsius until they were molten liquid, and they were not allowed to exceed 600 degrees Celsius because our clathrate decomposes at about 620 degrees Celsius. And after vigorous stirring, the resulting alloy was cooled and then analyzed using differential scattering telemetry and scanning electron microscope. And then this alloy was again heated until liquid again, and the appropriate amount of silicon clathrates were added to it, and then mixed again. This is held near 555 degrees for, in the case of aluminum-germanium, for several hours to ensure the complete reaction of germanium. And these final alloys were again analyzed using differential scanning telemetry, scanning electron microscope, and X-ray diffraction. And this is just a list of different instruments we used. Mostly it was differential scanning telemetry and the scanning electron microscope with the energy dispersive scattering, which allowed us to find the compositions to the nearest thousandth of a percent of our alloys. And clathrates are open framework structures made of silicon and germanium cages. They have excellent thermoelectric properties, and they're used right now to be utilized in solar panels, transistors, and a lot of upcoming technology. And these are just the components that make up a single unitary cubic cell of clathrates. There again is just a diagram of the structure of our silicon-136 clathrate that we were studying in particular. And these were made through the decomposition of sodium silicide in vacuum at nearly 380 degrees Celsius, and it decomposed into two products, but we're focusing on silicon-136 clathrate, which is obtained as a very fine powder. But we can't use these powders for any thermoelectric applications, really, so our goal was to produce larger crystals. And this is a phase diagram of our clathrate showing that it decomposes about 624 degrees Celsius right there. So any experiment that we did had to be conducted under that. And then all of our alloys had to melt below roughly 500 degrees Celsius. This is our aluminum-zinc phase diagram on the left, showing the eutectic point where we're studying, which is the lowest melting point where it's straight from a solid to a liquid phase. And for aluminum-zinc, that was about 380 degrees Celsius, and our aluminum-germanium, it happened at about 420 degrees Celsius. And that's just the aluminum-silicon phase diagram. And the same thing, it's melting at a much higher temperature, about 577 degrees Celsius. Our preliminary results indicated that the aluminum and zinc alloy was not suitable for this case because the clathrate had very low solubility, and it actually, in fact, did not wet and was not miscible. But since germanium forms an ideal solution with silicon, and silicon forms a eutectic alloy with aluminum, the clathrate should be more soluble in aluminum-germanium eutectic alloys. And these are just some scanning electron microscope images of our first aluminum-germanium alloy. And we use the scanning, the dispersive scattering energy, actually, to determine these compositions. And for the aluminum-germanium, it's roughly about 53.5% germanium to aluminum. This is our first phase diagram for the aluminum-zinc eutectic alloy without the clathrate, and we see that it melts at roughly 395 degrees. And upon adding and melting the clathrate, we did not see much change at all, and in fact melted at 398 degrees Celsius. And this is due to the fact that the clathrate was not miscible in aluminum-zinc, so we noticed very little change. Now for the aluminum-germanium eutectic alloy, it was slightly off the eutectic point, and it's a little bit more germanium than we intended. So we got 444 degrees was a melting point instead of 420. And once we added the clathrate, we did notice very little change, but it was in fact miscible this time. But We got everything done at 445 degrees. And this is just the germanium and silicone residue after we dissolved all of the aluminum in hydrochloric acid. And this shows that there was no phase transition, even ramped to 700 degrees Celsius. Our central problem was that we needed to find out if the silicone clathrate was decomposing when it was actually melting. And when silicone clathrate decomposes, it decomposes to elemental silicone, and the properties are a lot different for this and does not carry the electrothermal properties that we were intending. So in order to see if it was decomposing, we had to use X-ray diffraction because differential scanning telemetry would not allow us to notice any difference between elemental silicone and silicone clathrate. So here we have this is actual X-ray diffraction, and what we're really focusing on is the region between 30 and 40 degrees where we notice a strong peak of the clathrate. And then, once we created our first aluminum-germanium alloy, including the clathrate, this was heated twice, and we noticed that in the region of 30 to 40, all those peaks are much, much less. And in fact, there's a new silicone peak right next to the germanium. This is basically essentially showing the same thing, but we dissolved the aluminum in hydrochloric acid and removed that peak. And you can clearly see here that between 30 and 40 degrees, there's absolutely no silicone clathrate, and it's all decomposed in elemental silicone. Which is very interesting because the silicone clathrate is not supposed to decompose until 620 degrees, and it never did reach that temperature, and we kept everything around 500, 550 degrees the entire time, but it still, in fact, did decompose. So, in conclusion, we have silicone clathrate does not dissolve in aluminum-zinc alloys because the aluminum and zinc alloy did not wet the clathrate. And notice that the clathrate did dissolve in aluminum-germanium alloy, however, it converts to elemental silicone. And this spontaneous conversion of silicone clathrate to elemental silicone upon contact with the liquid aluminum-germanium is a new type of phase transition, and it occurs well below the original melting point that we were expecting.